Good morning, everyone. We are going to get started in a minute. So today we are having a tutorial by Matthew Desange, Pepper Mart, and Jan Sisko on the partition communication. Jan is here in person. Matthew and Pepper are remote. So we will go ahead and get started in a minute. Matthew, would you start sharing the screen?
Sure. Yeah. Let me know when you when we're ready to get started.
Yeah, I think we are ready. So it's all yours. And if there are any questions from here, Jan will be the moderator to get those questions to you from the room. And obviously, if there are questions on the chat, you should be able to see them, or even Jan might point out that, hey, there is a question in the chat. Okay.
All right, sounds good.
All right, are we all ready to go? Okay, all right. Take away, Matthew.
All right. Hi, everyone. I'm Matthew Desange. I'm a staff member at Sandia National Labs, and we're me and my collaborators here are here to present our tutorial, Effective Multi-Threaded Communication for Next Generation Scientific Applications. Let's just start off with a brief schedule. So we're going to start off with an introduction to partition communication, which is this first chunk here. We're going to try doing an interactive session from 9:30 to 10. We have generally 2 activities planned for that to get some hands-on experience with partition communication, given that we're kind of doing a hybrid remote virtual thing, that we'll see how well that goes. We have a break scheduled from 10 to 10:30, after which we will come back for another info session on insights in how to adapt applications for partition communication, given by Pepper Martz, who has done a handful of application conversions that look at getting the data transfer as close to data completion as possible in a partitioned model. And then we'll have a second interactive session that will build on top of the first interactive session. And we'll conclude with Jan Sisko giving a talk on some advanced threading features in MPI. Switch slides. So this is an introduction to partition communication. So why partition communication? And what is partition communication? Well, as we've seen in the past few years, MPI use cases continue to evolve. We see more and more cores and hardware threads being added to CPUs, and threading and tasking models are drastically increasing the number of threads per process. And more than that, you start looking at accelerators, we start looking at many, many actors acting on or as a functional unit as a process. If we don't have threading, this leads to having a bunch of MPI processes. If you have to have a process per actor. Obviously, that's not where any of the scientific applications are going right now. We need threading. And given recent surveys, there's been a larger interest in using MPI for concurrent communication for a number of reasons. One of which is just ease of being able to call MPI from wherever you want. Others are optimizations, such as early bird communication, which we will get into later. So what's the problem with MP or multi-threaded MPI? Well, this is a simulation or an empirical measurement, actually, of the time to drain the matching queue if we start doing really fine-grained communication. And there's no data copy in this. There's no message transfer over the wire. This is just matching. And the gray box up here represents an area in which we expect, or is the, once we get past the required runtime of per iteration for some applications that we've talked to, right? So like, or particularly like mini-MD or lamps tries to make sure that each iteration time is under this gray box. Well, if all of that's taken up in message matching, that can be problematic for a small auxiliary piece of middleware. So obviously this isn't an acceptable solution. So we need something else. So what is partition communication? We want to allow many actors to contribute to the data, but we don't want to have this explosion of MPI operations. So with partition communication, we need to keep the number of logical messages the same. We don't want to expand the number of ranks because there's storage and addressing issues there. So we want to have many threads work together to assemble a single message. At that point, MPI only manages completion notification, and we have actor/action counts rather than thread level collectives. To do this, we also want to leverage a lot of the other stuff that's been done to optimize communication. Persistent style communication, which we'll get into more later, allows us to amortize away a lot of the setup costs for, this. This requires a different set of scenarios with, or a different calling structure than you're used to if you're starting off from point-to-point MPI. So the other thing is that we need to make sure that there's no heavy thread concurrency required, right? Because a lot of what ends up happening with current MPI implementations is that the instant you turn on, or at least previous MPI implementations, is that you'll turn on MPI thread multiple, and between having to manage data structures and locking and critical sections within MPI itself, your performance will degrade, especially as you get more and more threads. So we want to make sure that we keep the thread concurrency as light as possible. We leave the placement and management of the data to the user, and we aim to have a low overhead of knowledge that needs to be passed into the MPI library, particularly number of workers or number of chunks that can be individually or worked on by individual workers. There's no more data packing, there's some potential issues here that we'll get into later, but it might even be, as Pepper will get into, one of the major challenges of adapting this to applications is restructuring data structures so that you patch as you go, in a sense. This allows us to send structures as they become available. So what's the end goal here? We have a new version of overlap. We call this early bird communication, where early threads can start moving data right away. To that end, if we have a single laggard thread, such as one that is affected by load imbalance or some serial work or even system noise, the other threads can start progressing their communicate or the message before that data is available. And this can and has been implemented over RDMA to avoid message matching overheads and data placement overheads. In particular, if you looked at the original Fine Points paper, which is the first partition communication paper, that was implemented over MPI's RMA interface, which was mapping pretty directly to RDMA at the time. So going further into this, we have this concept of persistent partitioned buffers. We want to expose the ownership of a buffer is shared to MPI, where we describe the operation to be performed before contributing segments, which this means we need to know what we're doing ahead of time. We need to know a lot about what in traditional send receive, you have kind of hand over a buffer to MPI and tell it to do an iSend or iReceive, and then wait on that message for completion. At that which point, MPI kind of has ownership of that buffer to some degree. Which is to say, until between the time of the iSend and the waits or returning, the buffer state is potentially inconsistent, so that MPI can write a bunch of the message into the buffer. the with having persistent buffers, we can have a number of operations going on to write into the buffer from the application and have communication going on at the same time, which is one of the goals here, is to allow us to overlap that more. The MPI implementation shouldn't need to know what the application's doing underneath the hood, other than that there will be calls to say that the application has, or the part of the buffer has reached a consistent state. And so the MPI implementation doesn't need to know much other than how many times it will be called at the time of initialization for a partitioned communication. Threads are required to manage their own buffer ownership such that the buffer is valid. Basically, you can't, because there's this new dependency, you need to make sure that all of your computation is done and packed into the buffer before you mark it as ready to send. The result here is that MPI is thread agnostic with a minimal synchronization overhead. We can get this down to an atomic increment, which is the best kind of we can hope for in situations like this. Give me 2 seconds. All right. So let's walk through like the evolution to get your code from non-blocking to persistent to partition communication. So we start off with, MPI send, or MPI I send and MPI I receive. These are the non-blocking calls. You have to wait upon completion using the request given back to you from the I send. The key application points here are MPI I receive needs to be called as early as possible when that buffer is ready for data. An option is to have 2 buffers that alternate so that at the beginning of any iteration, the buffer is one of those 2 buffers is can be marked ready or passed to MPI I receive. And then we want to do an MPI I send as soon as the data in the buffer is complete. If we have computation that we can do between that I send and MPI wait, that's fantastic. That's a more traditional sense of overlap. But these are kind of the key principles that we want to operate under just from non-blocking. But what do we add for persistent communication? Okay, we need to have an additional step. We need to set up the operation. This moves, so let's back up a second. What is persistent communication? So we have this request object in non-blocking. What if we could reuse that? If we're doing the same operation network operation over and over and over again. If we're sending the same size of data from the same buffer, from the same count, to the same range, everything remains the same. Maybe we could amortize some of that cost. So persistent communication moves all of this up to an MPI send init, which then can be started where your iSend or iReceive would happen before. We still have to wait on completion at this point. That'll be constant. So that doesn't change. But there's a couple, changes to our application points here, which is while we have the send init and it can amortize some of the overheads, we're still doing point-to-point from start to wait, which is to say there's no message matching occurs based upon when start is called. And so every time that you reuse this, because you can reuse the start and wait calls every iteration, the send and receive will have to match again. And so that you'd still have to do eager versus rendezvous to and all the protocol stuff, because you don't necessarily know where the buffer is going to be placed, or you don't know which buffer or which memory region you're writing into. So let's move to partitions communication. And if anyone has questions, feel free to stop me. Jan will, and if you're there in person, Jan will bug me to stop. And then if you're online, I have the chat open. Partition communication changes a couple things about this. Start no longer moves any data. Instead of instead of that being the iSend equivalent, we now have it's more of a setup call. Instead, we have MPIP ready, which marks which is closer to our iSend equivalent, but it only marks a region of the buffer ready to send, or a partition. So all of our partitions are uniform in the number of items they contain, the data type, and the number of total partitions the buffer splitting it into. Another change is that a lot of the remote overhead is now moved into the initialization call, in the sense that we're no longer we match at MPI partition send and init. This has a number of benefits in terms of allowing us to have optimizations that read or that leverage the fact that we know where the remote buffer is on subsequent iterations, so that we don't have to do any renegotiation. The other key application point, which is one of the challenges of using partition communication as a whole, is that MPIP ready should be as close to data completion as possible. The earlier you can call P ready, the more time for overlap that you have. The more time for early bird communication that you have. So we've talked about the send side. I wanted to touch briefly on the receive side. Another call is MPIP arrived. This allows you to check to see if a part of the data has arrived. Receive side partitions are specified separately from the send side. Which means that we can have a handful of different scenarios, right? If we just want to have send side partitioning, it might make sense to have the receive side partitioning be 1. This allows us to reduce the amount of extra communication we have to do to notify, right? If we have to maintain state on both nodes for each receive partition to know if the receive or if a receive partition is complete, this greatly reduces our state. Another thing, would be to have the send and receive partitions equivalent. This is a case where if we have early computation that we can do, right? If we have part of the message show up and we can do useful work using that, this might be a good option there. This turns every partition into kind of its own individual message to some degree, because there's a one-to-one mapping on both sides. And then you can think of something in between, right, where we have a constant integer ratio between the two. There's really no reason to have more receive partitions than send partitions, because the network can't transfer more than if the network's limited by that. If you if you have more receive partitions than send partitions, there's no extra gain, because the send partitions determine the network traffic and what chunks can be transferred at a time. But having fewer receive partitions can reduce the amount of overhead of tracking state, while maintaining both the ability to do early bird communication and early computation. The caveat here is that MPI doesn't restrict you on this. These are kind of the 3 cases that make the most sense. But MPI will let you shoot yourself in the foot. MPI, if you want to have completely mismatched send and receive partitions, that as long as the kind of overall buffers line up, MPI will let you do that. But there's, a case to be made that there's a cost to the granularity of receive set partitioning. In one sense, it limits aggregation or the potential for aggregation underneath the hood. And it, as mentioned before, increases the demand on state tracking for completion. I wanted to mention this as well. Some might ask, this sounds like a lot of the stuff to be handled with MPI RMA. And that's true. RMA is MPI's one-sided interface, if you're not familiar. It can offer similar benefits as partition communication with a bit more flexibility in a sense. Because you can you create a window and use MPI put or get to transfer data, and the put and get commands or functions take in an offset and a length, so and don't have a required number of calls, which means you can send a subset of the data. You can have heterogeneous chunks or partitions to send. There's potential benefit here, but the real problem is that we've seen is that RMA is complicated. We have window creation is order dependent and is communicator-wide collective. It requires a lot more knowledge in each put and get command. The simultaneous puts can theoretically target the same memory, which can get really complicated and lead to non-deterministic results if you have either a bug in your code or something that does that for some reason. And there's a lot of different synchronization methods to manage memory epochs. Some of these have been deprecated or are being deprecated, because MPI 2 introduced a 3 different synchronization methods, and MPI 3 introduced a couple more. But what this comes down to more than anything else is that RMA is most likely for advanced programming, and might not provide a general solution for applications that might not be worth the trade-off with effort needed to implement. So what does partition communication provide over this is that it provides a simple two-sided interface that physicists are more familiar with, and builds from there. So using PartCom in an MPI program, things to keep in mind. You need to think about your data structures. Being able to have data structures be partitioned already, in a sense, have logical chunks that can be sent, can help with moving this into the communication phase. Balancing communication granularity with overlap. We have done a bunch of tests, and for a reasonable number of partitions, 32 to 64, there's a range of where partitioning performs really well. Below that, your partitions get too small and you're latency bound, and that might lead to performance problems. Above that, your a lot of applications can't take advantage of the extra time, so that there's a extra overhead still, and even with RDMA, of sending these as smaller messages. And so once we get to a certain size, you start to see the overheads again, because you're not gaining as much from the little bit of time that you have extra to do transfer. So what's MPI doing to help? It's important when you're designing your application to keep in mind what MPI may be doing to help. This will help get optimum performance. We want to, be conscious about overlap, send early and often, take advantage of noise in computation, whether that's some sort of system noise or load imbalance or serial work that we need to do. And we need to be mindful of overheads. There's a bunch of opportunities for optimizations. Where we can do more under the covers to make sure that this is better. There's a lot of the implementations that I'm aware of are very first pass at this point, which means that as time goes on, these code paths should get faster and be more performant over time. And to give you an idea of what you can expect from partition communication, we have some example performance results. In particular, we're using our RMA-based external implementation here and coming up with a number of different application profiles. If you look at the different graphs, so we're running this on KNL. We have some amount of compute time, which is the second number in there, which is simulated compute time. We have finally some amount of noise, right? This is all based on a model of a laddered thread. And the idea that one thread will be delayed by whatever the noise percent is. And so you can see from a lot of this stuff, when we have noise and a larger compute volume, multi-send, which is just breaking it into a bunch of individual I-sends and I-receives, has a performance benefit. But when we start using partition communication, which is called fine points, so these are pulled from the fine points paper, we can get rid of a lot of the overhead. And we start to see a benefit in our available or our perceived bandwidth, which is the bandwidth or as compared to what we would have seen if we had waited till all the threads gathered before, in a BSP model where we have compute thread barrier communication. So the big takeaways here are partition communication is useful for concurrent programming models. We want to send data as close to complete or computation as possible. We we're not, partition communication is not for bulk synchronous models. And we are actively looking at how to support accelerators and GPUs in future iterations of this. With that, that's the end of my info session. Does anyone have any questions before we move on?
Hi, Matthew. This is Jan speaking. I'm looking at the audience right now. And do we have any questions? Let me see. There is a chat window here. I think in the chat window, there is nothing of relevance here.
Okay.
So, Matthew, you can either proceed or hand over to Pepper if you like.
Okay. Let me switch what I'm sharing. We're running a little bit behind, and so we may need to speed through this. All right, so let me stop sharing real quick. All right, and then I can start sharing. All right. Oh, I should. All right. Well, that's fine. All right. All right. So the big thing that Jan, is Puri still there? All right. All right. So one of the things that we're going to look at is trying to get some hands-on experience with MPI PCL, in particular, or partition communication. Puri, Tony et al. Have come up with a external library that they have available. I'm not exactly sure how to access it for the general public right now, which is MPI-PCL. So we can start looking at this. Where a lot of the tools in here are the same as you'd see in the real version, like OpenMPI. Let me see here. Oh, yeah, that would be the one. I was looking for that earlier. So if we grab this, I have, let me make sure. And oh yeah, I will do that in a second. Is that a good font size, Jan?
Yes, it's perfect.
So, we're looking at, this is your, or if you go to github/mpi-advance/mpipcl, you can get the, or MPI Pitl. It's a relatively lightweight library. And if I just load an OpenMPI real quick. This is kind of one of the ways that we can access what's that? Partition communication currently. There is a way to get it in mpitch, I believe, and I know that the current implementation in OpenMPI is available in the 5.0 release branch, or in the not the release branch, the PRs. So the it's set to be released in 5.0, and you can access it through the GitHub. But this is probably the simplest way for most people to access it at the moment, because you can use it on top of any modern MPI implementation. And if we I don't have CMake on here. If we go to kind of the source code of this, we can start looking at what makes MPI Pitl work under the hood. The big thing here is that all of MPI Pitl or MPI Pitl starts works on persistent communication. So let me see if I can find and so you have a number of starts and requests in it that you can look through. Unfortunately, we don't have a huge amount of time to do. Why am I to start building anything? But if we start looking through the examples, we can start seeing how to structure this in the sense of we need to start by having these p-send inits on a mallet buffer. We can start, so we could theoretically have an iteration loop here. But if we do some sort of simple computation, if we wanted to, if each thread was working on individual buffers, and each buffer was being set individually, we can then try P ready on the partition of the buffer that's being set up. And it's similar on the other side in terms of we can, once all the P readies happen, we wait for completion. We can check the buffer for correctness. I think I need to get some stuff ironed out for interactive session 2. So if we want to go to, there's a break scheduled starting in about 9 minutes. So if we want to start that a little bit early, we'll reconvene at, I'm trying to do math on, it should be 10:30 there, right, Jan?
Yes.
So let's reconvene at 10:30, and Pepper will do his info session, and I'll get some stuff ironed out for interactive session 2. So thanks everybody, and see you in a little bit. Enjoy the break.